only the expected value. Now if you go and try to what we call like risk-averse robust solution, so in this case here, I try to include also the variance term with me as part of my objective function. So I'm trying to manage to optimize the expected value of the objective function and also the variance. Right? So when this performance doesn't keep very much from my optimal solution, and I use a weight value here. So this is a weight that I will be experimenting with to see what is the best way, could be maybe problem dependent, to see like if you're trying to minimize the expected value also and include the variance, you can include other term here to represent the variation of the distribution. Here for this one we included the variance, but you can include any other solution. So this takes us back to like now, this is how the system will look like. So you have again your estimator, which is this is supposed to be running in real time, minute by minute, mimicking what happened in reality. So at any point in time, if you are trying to predict, we get a snapshot. We capture like snapshot for where are the vehicles, right? Where they are going. So we take a snapshot to be the initial condition for my predictor. Right? So we take a snapshot, put it in the memory, and this becomes my initial condition here. So we don't start from an empty network, right? This is what we are doing here. And then we try very quickly try to come with a scheme, right? And then you go implement the scheme in, of course, in your simulator that replicate the real world, and also the real world. This goes into the real world, and then at the same time go to the simulator. So we are trying to make this one consistent as much as you can with the real world. Of course, there could be some real-world data that we are receiving. We are not activating this part in this paper here, but we could be real-world data that we are receiving to ensure consistency always between your estimator and the real world. Right? But this part we are not activating it in this work here. But this part is interesting here. What I'm showing here is that, so I want to look at the performance of the system. It's like a dynamic system, right? I'm coming up with a scheme, implementing it, things changes, I go predict again, come up with a scheme based on my best knowledge of the system, right? And I try to be robust and all that, come up with a scheme, put it again in the system, and I keep doing this, right? So now how can I look at the performance of the system? You know, like when we're doing offline work, we used to go like, look at my horizon, capture what's happening for all travelers, get an average, and this is average travel time in the network, right? Here we come up with something different. This is a real-time system. We're trying to give the operator like a real-time number to look at to see if what is going on really improving the system or not, improving the network or not. So what we're doing at any point in time, we go back 30 minutes. We go back 30 minutes and they get the total travel time in the network, right, for this last 30 minutes, based on the actions that I keep doing, and I keep repeating this. So in another 5 minutes, I roll again, I look for 30 minutes. So any travelers existed in the network in those 30 minutes, I collect the statistics about them and I generate a number. So the results that I'll be showing is kind of like, yeah, it's like time varying total travel time in the network based on what I'm doing here every 5 minutes, the MOVs that we are generating every 5 minutes. Any questions here? Something? Yes?
For a non-specialist, can you explain what a traffic management scheme would look like and how it would be?
Yes, this is exactly my next slide.
Oh.
This is exactly my next slide. So now, yes, you are saying that you are building a scheme. What is a scheme? Like if you're talking like for the ICM or for the active transportation demand management applications, scheme is an integrated scheme. You can include in it any strategy that you think it might work well, right? So here we are exploring 3 strategies together. The first one of them is we do what we call dynamic signal timing. So I can, for these 30 minutes, I can come up with a timing plan for these 30 minutes, right? In addition to that, I can also, if I see like accident happening downstream, I can provide information to some travelers to divert. So we use a dynamic sign, the information on the dynamic sign to reroute the traffic. So this is another strategy that we're using, and the percentage of traffic that we divert, we assume we have a control on that in the simulation runs. Another one here is you can do like ramp metering. So you can test ramp metering. You can do any strategy that you think it might work in a combination like this. for the analysis here, we say, let's try to think of these three strategies together, like random metering with signal timing with dynamic routing, and see how they work. So the scheme here means that I'll try to come with, for this horizon edge that I'm looking ahead for, I'll try to build a scheme that integrates these three strategies. So I define traffic lights that I can adjust their timing. I define random meters that I can adjust their inflow rate to the freeway, and also I adjust where are my DMS, my dynamic signs, and where are the ramps that I can use to divert the traffic. So this is part of the solutions that we're trying to come up with. So here we are trying to optimize these schemes, right? If you remember in my slide here, I'm trying to look like a scheme, trying to find a scheme that by star I'm putting this is my optimal scheme that will optimize for me this Q2, right? This is like if you're going recipe neutral, and if you are going just recipe neutral, you just look at the expected value. So I'm looking for an optimal scheme here. To be able to optimize the optimal scheme is like considering this whole like large number of intersections that we have, all the ramps. It's like if you're trying to do it like optimally, like formulated as a mathematical program, mixed integer or something, it could be very challenging. Right? So what we thought here is, how about can use like a meta search heuristic, like something like genetic algorithm. And this is the idea here. We went and say, okay, how can I take a scheme like this and model it as a chromosome? Right? This is what we are doing here. So if this is one intersection, so this is like, here I'm showing like what I'm doing for one intersection. Assume for each intersection, I have 3 pre-approved plans. I talked with the city people and say, yes, for that intersection, you can apply timing plan 1, timing plan 2, timing plan 3. Don't invent beyond those 3 plans, right? So if I have 3 plans like this, and I have 1 here and 0 here, so means in this scheme, I'm activating action number 1 or plan number 1. Right? Same thing if you have a dynamic sign, and in this dynamic sign, you could have multiple actions that you can take, you choose one of them. Right? Same thing for the random meter, you choose one action. So this is here represent how we represent a scheme, right? Using genetic algorithm. You can now have another scheme like this, and then you can, so this is like first generation, if you are familiar, it's kind of like an iterative procedure. You start by building a set of schemes, saying these are my best population, and then I try to do like a crossover and mutation generation after generation. And when I'm doing this, I'm looking at the fitness of each one of those. Fitness here means what? What means the fitness of a scheme here? The performance, yes. So if you are implementing this scheme, what is the fitness? How it really help in reducing the travel time? Right. So whenever we have a scheme here, you need to compute J for it. The travel time, right? The total travel time in the system. But remember, this is not my objective. I'm trying to find something that minimizes Q1 or Q2, not minimize J. Right? So even if you go and compute for me, like if you come up with a scheme, so I'm coming up with a scheme here, I go simulate that scheme, I come up with J. Right? But this J is still not my fitness. What's my fitness here? So I have a scheme. I go try this scheme with all operation scenarios that I have from my distribution, right, of operation scenarios. So I have a scheme number, we call it by one of the schemes that I generated in the previous slide. And I have operation scenario S1, operation scenario S2, operation scenario S3, right? What an operation scenario here? What operation scenario could be?
Different combinations.
Yeah, maybe different demand level, maybe with rainy condition. Right? This is an operation scenario, and it has a certain probability, B1, or maybe like it could be like an accident with this demand level, low demand with a severe incident. Right? You could have different combinations of all that. So we call it like those are operation scenarios. So whenever you look at operation scenario, you have a scheme. So we go and we try to estimate what is the performance of that combination of scheme and operation scenario. Right? So this is what we're doing here. How we compute this G? Actually, we go like simulated. So we go and simulate. If this is the scheme and this is the operation scenario, go simulate it using your prediction module and they give me what is G. And repeat this again for all operational scenarios. Once you do that, you are ready now to compute the fitness. Because remember, my fitness here is like I was looking for the expected value, and I was looking for the variance across all operational scenarios. So for each scheme I'm generating using the genetic algorithm, I go and compute this number here. This is the fitness. This is something that I'm trying to minimize. So when I'm going iteration after iteration, I'm trying to keep the schemes that minimize this number for me, right? Because these are good in terms of the expected value and also good in terms of the variation. Clear to here? Clear? Any questions? So I'll stop here for a second, and for the last 2 hours we have been talking about this model here, direct, which is, this is the main simulation model that we are using to kind of like build the estimation module and build the prediction module, right? So we use a dynamic traffic assignment model here. This model, direct stands for dynamic intermodal routing environment for control and telematics. It's kind of like branched out of DynaSmart, but the good things about it, it's written totally in Java, object-oriented design, very clean structure. But as any dynamic traffic assignment model, it captures the interaction between the travel demand and network supply, as we're saying. Like you have a certain scheme, a certain operational scenario, you try to get the interaction between these two and they come up with the performance. So this is kind of the idea here. But another good advantage of it, it's like a multimodal system. It's so we capture the private cars, the transit, the intermodal trips. So this is part of the structure of the model. We have been using this model for the last 10 years almost in different projects, and we looked at different people approaching us to look at, especially for the ICM, for the active transportation, then we tried many strategies to test if the model is good for these strategies. Of course, this is a mesoscopic model, a little bit different from macro. If you are familiar with macro, this is more of mesoscopic, so the resolution is higher a little bit than microscopic. Microscopic capture at 0.1 second resolution. Here we are capturing the traffic dynamics at 6-second resolution. So it's a little bit different, but for the purpose of what we are doing here, yes, we are trying to get like you're modeling a regional network, right? I'm not modeling a facility or like a couple of intersections together. I'm looking at, as you will see right now, as a huge corridor. So mesoscopic models like this, PTA-based model like this will help in getting me some information about the performance without really on the expense of the computation part. This is like give you like an overview of the main structure of the simulator. So it has like a demand generation component. So as an input, it takes the time-dependent demand metrics for all travelers. And information also about the traveler distributions, how much have access to en route information, pre-trip information, willingness to use transit. Some of this information are here. And then the route multi choice assignment. So this is how we assign those generated travelers to routes. So we have a short space algorithm that's running, generate the shortest route between every origin and destination pair. Also look at if the transit options, it captures the transit option. It looks also at intermodality. So if you have a park and ride, so it gets all this set of routes, give it to the traveler compare between the cost of all these routes, and based on the preferences also that we generate for this traveler, the traveler chooses a route. Once we know the route that the traveler is choosing, we start to go and do the simulation. So here, like is as I said, a mesoscopic simulation. So it moves the vehicles like with average speed, but it's lane-based, not link-based. So we have for each lane, we have an average density that's updated every 6 seconds. We have an average speed based on that density. So we use modified green shield model here to every 6 seconds, based on the number of vehicles on the lane, we compute the density. After that, we get the speed, and then we move the vehicles with this average speed, right? And then if the vehicle moves to a next link, so we track here the demand that we have here is traveler-based, it's not vehicle-based. So in our model, we track travelers and vehicles. So both of them, we have tracked the traveler as when they start their trip till they reach their final destination. So this gives you about the test bed that we'll be sharing with you some of the results that we have. So this is like here in downtown Dallas here. And this is one of the busy commute corridors called US 75, goes from downtown Dallas, goes through multiple cities, city of Dallas, Richardson, Leno. So this is the commute corridor. SMU is located somewhere here. So this is like considered to be our corridor. So we have been working with this network for a while since we started the ICM project with DART and with USDOT. This was a test bed that DART proposed to work on. The network, I don't have statistics here, but as you see, this is the details of the network. It has 2 million travelers per day. To get an idea about the level of congestion that we have here, it goes about 20 miles. It goes about 20 miles from this is the down, like south here is the downtown, goes to the north suburbs, about 20-mile in length. A scenario that we are modeling here, so we are considering a non-recurrent congestion when you have an incident. This incident is for one, it's like a severe incident, closing 2 lanes for 1 hour, and it's in the northbound, which the northbound, the traffic usually in the morning is like heavy southbound, in the afternoon it's a heavy northbound. So we are modeling an evening peak. In the results that we're showing here, we are modeling an evening peak with severe incident like this. This is typical location where incident happen. Like this, here is a big interchange here, right? So the traffic that's coming down from the interchange with the traffic coming from the south with the weaving. So this is typical location where we observe this, and this is my daily commute, so I'm suffering with this condition every day. So before I showing the results here, people of course ask like genetics, yeah, you're not doing it to optimally, or this is like a heuristic. So what I'm showing here, I'm showing like the convergence pattern at one stage. So here, like I'm showing actually at 6 different stages, different times, and I'm showing like how the convergence happen, right? So you are coming up with a scheme, and then you get the fitness of that scheme, and then you go to next generation. So here I'm showing the generation ID and how the fitness is improving, right? And you can see here like within 10 generations we are stabilizing. 10 generations, we kind of like stabilizing here. So we decided that in all experiments, we're going to stop at 5, just to speed up things. So at each, for the genetic algorithm that I showed here, we start by, so this is here case when we're doing the W equals 0, so this is the risk neutral case when we don't have variance. Also, we looked at it when we have W equal 1, just to look at the variant, how the convergence pattern look like. So we're comfortable that if we go with 5, at least we got most of the performance that we are looking at. So also to get an idea about the computational time required here. Here we started like at each stage, when I'm rolling every 5 or 10 minutes. I started by 20 initial schemes. So those schemes here were for this horizon, for this edge, we come up with 20 schemes as I showed here. Right? And then, so this is my initial population, we get like a large population a little bit, but we do 5 generations after that, and we limit the number of schemes in each generation to 5. So in each stage, we have 45 schemes that were evaluated. If you multiply that by the number of operation scenarios, so this is a huge number of simulations that we are doing. Like 45 schemes. On average, if you say that I have 5 operation scenarios, so this is like about like 5 by 50, about like 250 simulation runs just every 5 minutes. So the results that I'm showing here, I'm showing like the results of traditional versus robust DSS. I'm trying to show like the one that we assume perfect prediction versus now, no, it's not perfect. We'll show that. Also, we'll look at the availability of information on the distribution of the operation scenario. We're going to look at that. You know, one of the assumptions that we made at the beginning that the two distributions are identical. So what I'm showing here, I'm showing that we looked at the operation scenarios. So I came up with 2 operation scenarios, and the operation scenarios that we played with here in terms of demand, different level of demands. So this one here showing like this is the variance of this distribution, is a small variance. So I have like here I'm showing it for a single OD pair. How the demand changes from, could be like 112 number of trips between this OD pair, goes to 125, so this is small variance. Here I'm showing when the variance is wider a little bit. So I'm trying to see my robust solution is more effective in a case like this or in a case like this, when the variation in the operation condition is constrained by nature, or when it's, no, there is huge variation in the operation conditions. So this one here is showing us the two extreme points. What I'm showing here is that the curve here is showing the total travel time under the do nothing, when I'm not activating the traffic management. And this here, blue bars here, showing the saving in the travel time, the percentage saving in the travel time. So this case here, I'm assuming that the predictions that I'm doing is consistent with the real world. So in this case, you don't need robust here, right? This is one case here. And this case here also is like, the prediction could be different from the real world. But again, I'm not activating the robust thing. So this could be like when you are very lucky, right? You predicted something and this is what happened. And this is when you are unlucky, right? You can see the difference here. Here is the total, we kind of like capture the total travel time saving here is like about 12,000, here about 45,000, so 3 times, range 3 times. So, but again here, no robust here. So our expectation where the robust would come. So if like now you are taking a case like this, right? This is the problem that you're trying to deal with. The prediction is different from reality, so you are trying to come up with a robust solution. But where do you expect the performance to be? We expect to be between these two, right? This is exactly what happened here. So when we see here, so we kind of like, again, the predicted condition mismatches actual condition, but we activated the robust decision support system. So in this case here, you can see the total travel time saving here is about 33,000 minutes, something in between. So this gives you an idea